Hi there, my name is Conor Meehan and I'm a Customer Success Manager at Silico. In this short video I'm going to walk you through how to use the Lookup Tables function in Silico. So lookup tables are a way of specifying the relationship between two variables in a custom function. Sometimes relationships between variables can be quite complex. For example, imagine you want your model to capture how the price of a good will affect its demand. Or you might want to model how a change in a company's workload will affect its attrition rate. These relationships are highly nonlinear, meaning that a change in the affecting variable, say price, will result in a disproportionate change in the affected variable, say demand. So lookup tables capture these complex relationships without the need to create complex equations, and as their name suggests, they simply look up the value of an outcome variable in a table that maps the values of the input variable to the outcome variable. So we can ground this in example by continuing our model of the drinks company from our other videos. Okay, so in that model we made projections about how our total units sold, or total drinks sold over the next year will be determined by the number of stores that we're stocked in, the number of stores that sell our product, and the rate of sale within those stores. So by that we mean the drinks sold per store per week. So far we have simply assumed a rate of sale of 10 drinks per store per week, and we haven't included any factors that might impact this or change it over time. So to make our model more realistic, we can introduce at least one factor which is likely to impact the rate of sale, which is price. So as we know, consumers are highly price sensitive, especially for consumables like soft drinks, and if we increase our price, it's likely to result in a lower rate of sale. At the same time, there might be thresholds within this relationship. If our competitor's retail price is currently €2 per drink, and we increase our price from €2 to €2.10, this will likely have a bigger impact on the rate of sale than if we increased it from, let's say, 2.240 to 250. So this means that the rate of sale is, the relationship between the price and the rate of sale is highly nonlinear. As such, instead of representing how price impacts the rate of sale through writing a typical equation, we can better represent it using a lookup table. So we can use the lookup table to specify the rate of sale, so how many drinks sold per store per week for a given price. Okay, so the first thing to do here is to introduce price as a variable in the model. So if we right click here, select create variable, and we're going to call this the retail price. So this is the price, the euro, that the consumer will pay per drink. And let's just say that at the moment the stores are charging €2 per drink that we sell. So the next stage is to introduce the lookup table. So to do that, we right click here and we select create lookup table, or we can use the shortcut of pressing L. And what this is going to do is specify a given rate of sale for a given retail price. So we can call this lookup table. Click in here, we see the inspector, which is different to the inspectors that we have for variables. And we'll walk you through step by step now what each of these things mean essentially. So for the name, we're going to set this as price versus rate of sale, because for a given price it's going to give us a rate of sale. We won't need to put anything in the stub here. And then we can look at the other parts of the lookup table functions. So before we do that, I think it's important to just reflect on what we're trying to do with this lookup table function. So again, we're specifying what a rate of sale will be for a given price. And this can be based on past data, it can be based on assumptions guided by some research or common sense. And of course, we likely won't have the perfect data for determining how a change in price will affect the rate of sale, but that doesn't mean that we should exclude it from our model. So excluding it would essentially be saying that there is no such relationship, that a change in price won't affect the rate of sale, whereas including it, at least if we do so in a reasonable way, will improve the accuracy of our model rather than disimprove it. So with that in mind, let's look at how we can actually use lookup tables in Silico. Okay, so the first step here is to set the start and end values. So these specify the range of input values for which we will be setting outputs. So in this case, the input will be price. So the start is going to be basically what's the lowest price we would consider charging in this case. So what's the lowest price we want to set outputs for. So let's say that we're considering charging $1.50 would be the lowest price that we would consider charging. So we'll put $1.50 as a start. And the end then would be what's the kind of highest range input value that we want to set outputs for. So let's say that the highest price we would consider charging is €4. So for that reason we'll set the end as 4. And you can see that that changes the x-axis on the lookup function here. Okay, so the next step is to set the min and max variables down here. So that will basically specify what's the lowest and highest output value that we can imagine here. So in this case, the output value will be the rate of sale. So we can imagine what's the lowest rate of sale possible and also what's the highest rate of sale possible. That will determine what the min and max value should be here. So obviously it's possible to have a rate of sale of 0. If you charge too high a price, no one's going to buy the drink. So we'll have the min set to 0, and then the max we can consider what's the highest possible rate of sale that we could have. So even if we gave the drink away for free, within the stores, there's still only a maximum rate of sale that we would have. And in this case, let's say that would be 30 drinks per store per week. So we can see how that affects here the y-axis. So essentially we're saying for a given rate of inputs, so the price between 1.5 and 4, determined by the start and the end values, what's the range of output values, which we're saying can be between 0 and 30 for a given rate of sale. Okay, so the next step is to set the number of steps. So what that means essentially, if this is set to 10, for example, it means that for the given range of 1.5 to 4, so the given range of inputs, there'll be 10 different values to enter in between those. Whereas, for example, if we were to set this to 1, then there's now just the extremes of the range, so there's 1.5 and 4. So for simplicity, let's do this first. Let's enter as if there's one step between. So for a price of 1.5, what is the given lookup value going to be? So let's say that data says that if we were to charge a price of 1.5, our rate of sale would be 30, let's say. Whereas if we were to charge the price of 4, that's too expensive and therefore no one's going to buy a drink, and we're going to set a rate of sale of 0 for that. So you can see how that changes the line here. And what this is basically saying, as you can see, is the higher the price you charge, the lower the rate of sale will be. And there's also linear interpolation in between. So for all points in between 1.5 and 4, the software is giving a value based on linear interpolation. So for example, this value of a price of 2.5 will give a rate of sale of about 17 drinks per store per week, for example. And anything above €4 will also be 0, and also anything below 1.5 will give a value of 30. So if we set the retail price at below 1.5, the lookup return value will be 30. Okay, so now that we've got that set up, let's have a look at how we actually make use of the lookup table. So we have to connect it up to the rate of sale. So we draw a connector between the input variable to the affected variable, and also the lookup function to the affected variable. So here we had a value just of 10 before. We can now remove that because this is going to become dynamically determined by other variables in the model. And the way that we use these lookup tables is first we click on the lookup table, so we click on price versus return of sale, and then in the brackets we choose what the input variable for that lookup table is going to be. So here we'll select retail price as the input, and we can see that for a price of €2, it's now returning 24 as the rate of sale. So that's because of this linear interpolation going on, whereas you see here, if it was 2, then the rate of sale we're saying here would be about 24. So we know that actually in reality this isn't a straight line between the two, because there's lots of non-linearities in this relationship. For example, if we're charging €2 and we switch to €2.10, there's going to be a bigger difference if that's what our competitors are charging than if we go from €2.40 to €2.50. So what we want to do now is actually introduce that complexity into this relationship, and to do that we'll have to have more steps basically in the model. Okay, so to capture this complexity, let's say that we want to be able to represent a lookup value for every 10-cent increase in price. So there are 25 such increments between 1.5 and 4. So for that reason, we'll set the steps to 25. So now we can see there's a 10-cent increment in price, and we can set a specific lookup value for that from 1.5 all the way to 4. So we know that at 1.5, the rate of sale that we're assuming would be 30. We know that at 4, that's too expensive a price, and the rate of sale we're assuming would be 0. We might also know, for example, that based on previous data, when we charged €2, the rate of sale would be 10 units per week in that case. And we might say, for example, that if our competitors were also charging €2, then if we were to reduce our price to 190, that might have a pretty significant effect on our rate of sale. So it might jump up to, let's say, 18. If we were to charge 180, it might be slightly less dramatic effect, so only an increase of 4, let's say, to 22. Then this might be 26, 28, etc. So we can kind of use whatever assumptions we want there. We might also assume that, let's say, the increase of price from 2 to €2.10, if we're now more expensive than our competitors, that might reduce our rate of sale down to 8. However, if we were to increase from €2.10 to €2.20, that might not have as significant effect because we were already more expensive than our competitor anyway. So that might only reduce our rate of sale to 7, and then we could say every kind of 10-cent increase might incrementally affect our rate of sale by reducing it by 1, and so on until we basically fill in the rest of the values. So we might say when we get to more extreme prices, that an increment, let's say from even 3 to 3.10 might be even less. So let's say from 270 to 280, instead of reducing it by a value of a rate of sale of 1, we reduce it by just 0.5. So from here on in, it might be like this, etc. So we can basically come up with all these different assumptions for how different rates of sale will give different prices will give different rates of sale, and the different assumptions that might be therein. Okay, so we've now completed that lookup table, and we can see here why we're describing this as a nonlinear relationship. Obviously, for a given price, there are varying different kind of effects on what the rate of sale will be. So we can see here, obviously, the change from 2 to 190 has quite a dramatic effect, whereas some of the other increments of 10 have a much less dramatic effect because there's less psychological barriers, such as comparison to competitor price, etc., for the consumer. So this can be used in various different ways. We could also have here, for example, employee workloads and how that affects attrition. So there might be kind of tipping points within that as well. And there's various different kind of relationships that we can use for lookup functions that are better represented by lookup functions to represent in our models. So again, just to show how this actually works within the model, you can see here now that we've set a price of 2 for that lookup function, because 2 was giving a rate of sale of 10. We can see that now this is returning a value of 10 here, whereas if we change this to 2.1, this gives a value of 8, which, as you remember, was what we set in the lookup table. Or if we set a price of 1.9, the rate of sale then changes to 18, which is also what we determined here. So we can see how basically changing different prices will result in different rates of sale. That basically covers how to use lookup functions. There's obviously various different categories and different ways that you can use them, but that's one of the basics. There is also ways where you can use 2 lookup functions at once to impact a kind of a relative change on a variable, and we'll explore that in another video series as well. But I hope that you found that useful. In the next video, we'll explore Silico's scenarios feature, and we'll look at how that scenarios feature could be used to find what the optimal price might be. So what the price might be which will give the highest revenues, so maintain a good price per unit, and at the same time keep volume of sales high as well. So thanks a lot for your time. I hope that's been useful, and take care.